In section 2.1, we're going to start off talking about the basics of functions and their graphs. Starting off with a few definitions here. First off, the so-called ordered pair is a shorthand way to denote the correspondence between objects. For example, Texas, USA in parentheses would denote an ordered pair. Ford, Mustang, or oftentimes we're using numbers like 4, 10, or X, Y refers to an ordered pair. A relation is a set of ordered pairs taken together. Here's an example would be car manufacturers with the different types and models of cars such as Ford Mustang, Toyota Camry, and Kia Soul, and so forth. Putting those ordered pairs together creates a relation. The domain of a relation is the set of all first objects in the ordered pairs. For instance, Ford, Toyota, and Kia would be the domain of the relation that we see above. The range is the set of all second objects in the ordered pairs, also thought of as outputs for the inputs from the domain. So in the case up above, the range would be Mustang, Camry, Soul, and so forth from each ordered pair. A function specifically is a relation in which each element of the domain corresponds to exactly one element in the range. So for most part, we're going to be talking about equations with variables, and we'll put numbers in often for the variables. Specifically for equations with two variables, if we get exactly one output, which is often called the dependent variable, usually y, for each input, which we usually refer to as the independent variable, or x, then the equation specifies a function. So the picture here shows x is the input to the function and y comes out of there as the output from the function. So we could plug in a 2, and let's say the function takes the 2 and gives us an 11 as an output. That would be the example of what we would see a function do. Take an input number and give us one number for output. However, it would not be a function if we were to say to put in a 2 and then get out two numbers like 11 and 19. Getting more than one output would no longer make what's happening here a function. So that's an example of not a function. Using ordered pairs, this is how we would write our input-output numbers. So the 2 plugs in, we get an 11 output would be 2, 11 as an ordered pair. For the not a function situation, it would look something like 2, 11 and 2, 19. So for a function, we could think of, for instance, a checkout machine which scans the barcode, and say it scans the barcode for eggs and gives a price of $1.50. This would be the example of a function. One input and we get one output from it. On the other hand, we would not expect to scan a product like eggs and get two different prices out at the same time. That's why this is not a function. It would not make sense in this case to see that happen. So we see functions all around when we have this correspondence between one thing and the function connects it to another thing. But we only get one output for each input that we plug in to the function. So looking at ordered pairs here, we're going to determine the domain, the range, and whether or not these ordered pairs connect to a function. In the first example, the domain is the first part of the ordered pairs. So if we look at those numbers, it would be the 1, 2, 3, and 4 would be the domain of this relation. The range is the second part of the ordered pairs. So we look at the numbers in the second part of each ordered pair and we see a 6, an 8, and a 9. We notice for each x input in the domain, there's exactly one number in the range for the output for each value of x. So this would be a function. Another way of noticing that is that no x's repeat in each of the ordered pairs. All the x numbers in the domain are all different numbers. And so that's what is characteristic here of a function. And the second set of ordered pairs, the domain would be the 6, the 8, and the 9. The range would be 1, 2, 3, 4. In this case, notice how the number 6 shows up twice in the domain. The x value repeats, which means that the number 6 gets assigned both a 1 and a 2 in the range. And so since 6 repeats in the domain, this is not a function. It would be the situation where an input of 6 gives us two numbers, 1 and a 2. Now in this example, what we're going to do is take a look at it as an equation and determine if the equation defines a y as a function of x. In order to check whether or not we have a function from this equation, we're going to solve the equation for y. So in the first one, 2x plus y equals 5. To solve for y, I'm going to subtract 2x over from both sides. That solves for y and makes it y equals 5 minus 2x. Now the question is this a function? If it's a function, then if I plug in a number for x, I should only get out one number for y. One input produces one output. We can verify that if we want to, if we just plug in some numbers for x. For instance, if we plug in -2 for x, and into the equation would look like 5 minus 2 times -2 would give us 5 plus 4, or 9. If we plugged in 0, it would be 5 minus 2 times 0, which would be 5 minus 0, or just 5. And so forth. If we plug in a +2, it would be 5 minus 2 times 2. 5 minus 4 would equal to 1. So we can see how each input number for x generates one output number for y. As a result, since each input only produces one output, this is a function. So this equation, y equals 5 minus 2x, would represent a function for x and y. Now for our next equation here, it says x plus y squared equals 4. So again, what we're going to do here to check whether or not we have a function is to solve for y. To do that, first thing I'll do is subtract the x over, turn this into y squared equals 4 minus x. Now since that's a y squared, we have to take the square root of this if we're going to solve it. And one of the things about solving equations is if we take the square root of both sides, we put plus or minus in front of the square root. Now we can cancel out the y squared and the square root to just leave it as y equals plus or minus the square root of 4 minus x. Now, does this equation represent a function is our next question. Like in the last situation, let's just take a number for x and see what happens when I plug that in and get out a number for y. In this case, let's start off with just say the number 0 for x. If I put a 0 for x, then y would equal to plus or minus square root 4 minus 0. Well, that would be the same thing as plus or minus the square root of 4, which is, square root of 4 is 2, so plus or minus 2. Well, in this case, now we're getting out two numbers. -2 and +2. Since one number for x makes two numbers for y, this equation is not a function. Another way of checking whether or not something is a function is through the vertical line test. The vertical line test connects to the graph of equations and functions, and it says that if a vertical line can be drawn intersecting a graph at more than one point, then the graph is not of a function. So it's a quick way of determining if something obviously is not a function or is a function. And so we're going to look at some pictures here to verify whether or not these graphs connect to functions by the vertical line test. The first one here, notice if I draw a vertical line through that graph, I can draw it and it can cross the graph at 3 different locations. So since that happens, this graph does not connect to a function. On the other hand, if we look at the one below that and I draw several vertical lines through the graph, notice how the vertical lines will only cross at one point each time. So this graph does represent the graph of a function and passes the vertical line test. The next one over also passes the vertical line test because vertical lines will only cross in one place each. On the other hand, the last one, the circle, does not pass the vertical line test. If I draw a vertical line there through it, you notice it will cross in more than one place. So looking at the graph, we can easily tell by the vertical line test whether or not a graph is generated by a function or is not coming from a function. Connected to the discussion of functions is the so-called function notation. Function notation is there to use letters like f, g, or h to give a name to the equation as a function. We write the function output as the letter of the function along with the independent variable. For example, we often write f of x in the place of y. This means we are using y equals f of x. This represents the output of the function called f using the value of x as its input to the function. So in our picture here, it shows x is being fed into the input of a function called f, and then f of x is the name which is given to the output of the function. So to show how function notation works, we're going to look at these two functions called f of x equals 2x and g of x equals 2x minus 3. We're going to graph them and determine how the two functions relate to each other with their graphs. So here what I've done is set up some tables so we can substitute some numbers in for x and calculate the numbers for the functions. Starting off with -2. If I was to put that here for x, it would look like f and then in parentheses -2. So I'm plugging in the number for x. 2 times -2 would give us -4. For 0, f in parentheses 0, pronounced f of 0, would equal to 2 times 0, or just 0. For 2, f of 2 would equal to 2 times 2, or 4. For the function g, if we plug in a 2, it would be g of -2, which would equal to 2 times -2 minus 3, which would equal to -7. For 0, g of 0 would equal to 2 times 0 minus 3, or -3. For 2, g of 2 would equal to 2 times 2 minus 3, which would be equal to 1. All right, now we're going to go ahead and graph these two functions with the numbers we have up above. So for f of x with -2, I got -4. So we're going to plot a point right there. For 0, it's 0. And for 2, it's at 4. So we have 3 points. In fact, this graph will just draw a straight line through the points. That'll be the function f of x equals 2x. For g of x, if I plug in -2, it's at -7. For 0, it's at -3. For 2, it's at 1. So it's also just going to be a straight line like so. For g of x is equal to 2x minus 3. So the big difference we can see between these two functions and their graph is the graph of g of x is the graph of f of x shifted down by 3, which agrees with the fact that g of x is just 2x minus 3 versus regular 2x. All the numbers get shifted down by the minus 3.